All right. In this video, we are going to study two ways of finding a solution to a system of linear equations: Cramer's rule and Gauss-Jordan elimination. Let me first introduce the basic idea about Cramer's rule with the example in the next slide. So here we are given pair of linear equations and two variables. And suppose we are looking for solutions x1 and x2. Because we have two equations and two variables, and if we rearrange this equation into a matrix form, the coefficient matrix is going to be 2 by 2. Okay. So first, let me rearrange this equation. So rewriting this equation into matrix form. Then I have 2 by 2 coefficient matrix and the variable matrix, and the two constants on the right hand side. Let me call this parameter matrix. All right, and then we are going to use matrix inversion method to find the solution x1 and x2. So we are going to pre-multiply by the inverse matrix of this 2 by 2. But for this purpose, we have to first check whether this matrix has an inverse. So regarding invertibility, we learned two conditions: non-singularity and non-zero determinant. But in case of 2 by 2, we have a nice formula for the determinant. So let me adopt a determinant test. So if I compute the determinant of this 2 by 2, first take two entries on the diagonal and compute the product. And the two entries on off diagonals, compute the product. And if we find the difference, that is negative 28, non-zero number, which means this matrix has an inverse matrix. So x1 and x2. Now we pre-multiply by the inverse matrix. On the right-hand side, then we get 5, 3, 6, negative 2 inverse, and the parameter matrix 3 and 8. And now we know how to compute the inverse matrix of 2 by 2. So the reciprocal of the determinant and the inverse matrix is going to be 2 by 2. And we switch the two entries on the diagonal and put negative signs on off diagonals. Okay, so this is the inverse matrix of coefficient matrix in this example. Then we are done. So x1, the first solution is going to be reciprocal of the determinant times the first row of the inverse and dot product parameter matrix. And x2, reciprocal of the determinant, now the second row of the inverse matrix and dot product parameter matrix. So this is a so-called matrix inversion method. So we first rearrange the equation into the matrix form and compute the inverse matrix. And then doing product gives us solutions x1 and x2. So it has a pros and cons. This method has a pros and cons. One advantage of this method is we can identify two solutions at one attempt. But the weakness of this method is usually it entails a heavy computational work. So matrix inversion method provides us a full characterization of solutions at the cost of some tedious computational work. In case of 2 by 2, computation is manageable because we have a nice closed form formula for the inverse matrix. But think about the example in the next slide. We have three equations and three variables. Now the coefficient matrix is going to be 3 by 3. And as we have seen one example in the previous video, computing the inverse of 3 by 3 entails a heavy computation work. We have to determine the determinant, and we have to find the adjoint matrix that consists of 9 cofactors, and etc. Okay. So the basic idea of Cramer's rule is, is there any other efficient way or practical way of finding solutions? The answer is yes. Especially this rule is quite useful when we are interested in one variable. So suppose we are not interested in the whole solutions, so the entire solutions. So we don't have to know x1, x2, x3 satisfying these 3 equations. Rather, we are interested in one specific variable, say x2. Okay. And the Cramer's rule tells us we don't have to go through the entire process of matrix inversion. Instead, there is a nice way of finding a solution with a less computational work. Yeah. So go back to the statement on page number 13, and here is Cramer's rule. We have n by n matrix, non-singular matrix A. So non-singular means this matrix A has an inverse matrix. And one parameter matrix B that is not 1 by n, but n by 1. So that's a typo. And I found several typos in this slide. I think I corrected almost them, but I found one more thing. Anyhow, so with this matrix B, matrix A forms a system of linear equations. So AX equals B. So here variable matrix should be n by 1 matrix, meaning that X has n variables from x1 to xn. And if we are not interested in the entire solutions, but interested in one specific solution, say kth solution, xk star. And Cramer's rule tells us we don't have to compute the entire inverse matrix of A, but the only thing we have to do to compute the determinant of these 2 matrices. First, we have to compute the determinant of the original matrix A regardless. And the determinant of the second, so this matrix is the same as the original matrix, except the kth column. So the first column is the same as the matrix A. Second, so all other columns are from the original matrix A, but the kth column is replaced by parameter matrix B. Okay, so let me call this matrix A star K. Okay, meaning that the kth column is replaced by parameter matrix B. Okay. And Cramer's rule tells us kth solution is going to be determinant of this matrix we obtain after replacement divided by determinant of the original matrix A. Okay, so the only thing we have to do for computing the kth solution is to compute these 2 determinants. So before I explain how we obtain this formula, let me first show you how to make use of this formula. Okay, so going back to the example 2 by 2. Suppose we are interested in the first variable, x1 star. So the first solution is, we put the determinant of original matrix A on the bottom, and we already computed that. It turns out that it is a negative 28. Okay. And A1 star, or A star 1. So now we replace the first column of matrix A by the parameter matrix. So the first column becomes 30 and 8. And second column is the same as matrix A, right? And whose determinant is negative 60 minus 24, so negative 84. Okay? So this is the first solution. And the second solution, we still have the determinant of matrix A on the bottom. Now we need to construct A star 2. So first column is the same as matrix A. Now the second column, instead of 3 and negative 2, we put in the parameter matrix 3 and 8. Okay. Then its determinant is 40 minus 180. So negative 140 on the top and negative 28 on the bottom. Okay, so what do you think? I mean, in case of 2 by 2, matrix inversion and Cramer's rule give us almost the same amount of computational work. But things will be different in case of 3 by 3. And suppose in this example, we look for the third solution, x3. Okay, then the coefficient matrix is now 3 by 3, so 7 and 10 and 6, right? And in order to find x3 star, we construct A star 3. So leave the first two columns alone and replace the third column by parameter matrix. Then by Cramer's rule, we can easily find the third solution. So determinant of A star 3 divided by determinant of the original matrix. Okay? So it's still 3 by 3, and we need to compute these two determinants, but that is much, much easier than and much more, simple than computing the inverse matrix of this 3 by 3, right? So I'm not going to compute these two determinants because this example is from the textbook. The determinant on the top, A star 3, that is negative 244, and determinant of the original matrix, negative 61. So it boils down number 4. Okay. All right, then let me illustrate how we obtain the formula, Cramer's rule. And the key idea can be best presented in the 3 by 3 case. Okay, so we have a 3 by 3 coefficient matrix and 3 variables and 3 constants on the top, on the right hand side. And using matrix inversion, we know x1, x2, x3. So let me call this matrix A. So A inverse times parameter matrix B. Then we learned how to compute inverse matrix. And suppose we are looking for the second variable, x2 star. And we have a multiplication on the right-hand side. And by the rule of multiplication between two matrices, the second variable is going to be the second row of the first matrix and dot product the first column of the second matrix. So x2 star, because A inverse is reciprocal of the determinant and the adjoint matrix, so adjoint of matrix A, and whose second row is going to be, so is determined by the second row of the adjoint. And remember, the adjoint of matrix A is the transpose of cofactor matrix. So because of this transposition, the second row of adjoint matrix A is going to be second column of the cofactor matrix, right? So the C super 2, second column of the cofactor matrix, has 3 entries, C sub 1, 2. So the cofactor, after eliminating the first row and second column, C sub 2, 2, eliminating the second row and second column, and 3, 2. Okay? And if we expand this dot product by using the definition of a dot product, and we have this expression. So summation of the product of each component. Okay? So B sub 1 times C sub 1, 2, and B sub 2 times C sub 2, 2, and so on. All right? And if we ponder about this expression, right? This is the Laplace expansion by the second column of matrix A star 2. Because A star 2 is, we leave the first and third column alone in the matrix A. And we replace the second column by a parameter matrix, right? And this is a Laplace expansion by the second column, because if we do Laplace expansion by the second column, we're going to eliminate this second column. So it doesn't affect, the Laplace expansion, because we are going to eliminate this second, right? And the remaining entries, so they will be the same as the original matrix. So these cofactors will be made of the same entries. So this dot product expression is going to be determinant of A star 2, because determinant is a Laplace expansion by one row or by one column. Okay. So, and divided by determinant of A. Okay. So this is how we obtain that formula. Similarly, X3 star is going to be the third row of the adjoint matrix, and dot product parameter matrix B. Then if we expand the dot product, that's going to be Laplace expansion by the third column of A star 3. So the X3 star is going to be determinant of A star 3 divided by determinant of matrix A. Okay, and the same rule, the same procedure applies to the first solution as well. Right? So this is how we get Cramer's rule. All right, and there is a little bit discussion about homogeneous equation system in the textbook. So let me mention a little bit about this. So homogeneous equation system is linear equation system, but the parameter matrix is given by zero vector. So all constants on the right-hand side are zeros. Okay, and we call this homogeneous system or homogeneous system. Okay, so using matrix forms, we can rewrite these equations into AX equals 0. This is a zero vector and zero matrices. N by 1, zero matrices. And for this type of system, we always have a solution, trivial solution, that is zero vector, zero matrix. By definition of zero matrix, no matter what this coefficient matrix is, multiplication gives us zero matrix. So we have this solution always, irrespective of this coefficient matrix. Okay? But sometimes this system, homogeneous system, has a non-trivial solution. So some entries are non-zero number. Okay? And that is called a non-trivial solution. So one natural question that arises is, when homogeneous equation or this system has a non-trivial solution. Okay? And this is linked to linear independence or linear dependence. Okay, I think we discussed linear independence vectors last week. So let me remind you of definition. So suppose we have the set of n vectors a1, an. Then we say the set of vectors is linearly dependent if one vector of these n vectors, so say a super n, the first vector, can be expressed as a linear combination of the others. So that means there is some non-zero numbers x2, x3, and all the way to xn. Okay, if these x, n minus 1x are, all zeros, then we don't say this is a linear combination unless some x's should be non-zero numbers. Okay? So the set of n vectors is linearly dependent if at least one vector of this n can be expressed as a linear combinations of the other. All right. Then if we can move this a super 1 to the right hand side, so negative a1, x2, a2, and we add all the way to xn, then the left hand side becomes zero vector. Okay, and we can think of this negative 1, x1, right? Then this is nothing but homogeneous equation system. Because, going back to slide, if we take a look at the first term of each equation, that is a super 1, so the first column of the coefficient matrix times x1, and second term of each equation is nothing but second column of matrix A times x2, and so on. Okay, so we have n vectors from a super n to a super n. So a super 1 to a super n. Okay, and then we have n coefficients from x1 to xn. So the homogeneous system has a non-trivial solution. So when the homogeneous system has a non-trivial solution, if and only if the set of vectors, column vectors, a super n to a super n is linearly dependent. All right, so because if the set of vectors is linearly dependent, then we have non-zero numbers x's that become the non-trivial solution of a homogeneous system. And one more thing we have to notice is if a homogeneous system has a non-trivial solution, so there is a non-zero vector, non-zero matrix x star satisfying this equation, then any scalar multiple is going to satisfy this equation as well. Say 2x star and 3x star, because they are scalar multiple, does not affect the right hand side. This is going to be 0 because it can be cancelled out. So that means the homogeneous system has infinitely many solutions. So once we find the non-trivial solution to homogeneous equation system, then we can anticipate there are infinitely many solutions. All right. Now let me illustrate the second way of finding solution to linear equation system. That is so-called Gauss-Jordan elimination. This method is reminiscent of the elimination way when we solve a simultaneous equation system. Okay, so the second way is to transform the augmented matrix into reduced row echelon form by means of elementary row operations. So we learned three types of row operations: row switching, row multiplication, and row addition. And when we attempted to find low echelon form matrix, we used row switching sometimes, but most times we use row addition. We never used row multiplication. That means each row can be divided by some scalar or can be multiplied by some scalar. Okay? But now for this Gauss-Jordan elimination, we have to transform the original matrix into the reduced row echelon form. So as the word reduced suggests, we have to simplify that low echelon form a little bit further. Okay, so the one low echelon form matrix is said to be in the reduced form if the first non-zero entry in each row, that is called pivot, is a number 1. So that is the first condition for one matrix to be in the reduced form. And the second condition is each column containing a pivot contains no other non-zero entries. Okay, so in order to transform one matrix into reduced form, we have to check whether these two conditions are violated or met. So think about the third example here. This matrix is not reduced form because it violates the first condition. The first non-zero number in the first row is not 1. This is going to be pivot of the first row. Pivot is defined as the first non-zero entry in each row. But pivot is not number 1, but number 7. So it does not satisfy the first condition, so it's not a reduced form. And the third condition, the first non-zero number in each row are number 1. Okay, so satisfying the first condition, but violates the second because think about the second column. This column contains one pivot, right? Pivot in the second row, but also contains other non-zero number 7. Okay, so it does not satisfy the second condition, so it's not a reduced form either. So on the other hand, the first two matrices are reduced form. Identity matrix, that is a most desired matrix, so it is a reduced form. Each pivot is a number 1, and each column has just one pivot, and the other entries are zeros, so satisfies the second conditions as well. And the second example, we have a number 3 here, but that is not a pivot because the first non-zero entry in the second row is number 1. So satisfying the first condition. And the second condition, because a third column does not have any pivot, so it has no bite. It has nothing to do with the second condition. So it is a reduced form. Okay, so now let me show you how this method is applied to finding a solution to a linear equation system. So I was planning to revisit the previous example, so how to find the solutions to these linear equations, but it turns out that, this is hell. I mean, it has, so I gave it a shot to this example by using the Gauss-Jordan elimination, but turns out that, this is a very complicated. So let me show you a way simple example. So way more simple example. So in this note, so suppose we have a system of 3 equations and 3 variables. Five x1, 7x2, 5x3, and x1, 4x2, 2x3, and 8. Okay. Then coefficient matrix is A is negative 3, 2, negative 6, 5, 7, negative 5, 1, 4, negative 2. Okay, I just collect coefficients in each equation. That is 1. And parameter matrix, that is a 6, 6, 8. Okay. And then we add one more column to this coefficient matrix to construct a augmented matrix. So this is called augmented matrix associated with this system. All right. Then the how the Gaussian how Gauss-Jordan elimination method works. We transform this coefficient matrix into reduced form. So reduced row echelon form. All right. So first we need a pivot number 1 in the first row. Okay. So let me switch the third row and the first row. Okay. Then we get 1, 4, negative 2, and 8 on the top in the first row. All right. 10. Okay. Because we have to eliminate number 5 in the second. And now number 3, that is in the third row. So, but we have to kill these two. How do you do that? Now we multiply negative 5. So we multiply the first row by negative 5. Then we can eliminate this number 5 by adding to the second row. Then the second row becomes 0. The first entry is 0. The second entry is 7 minus 20, 4 times negative 5. So negative 13. The third one, 5. And the last one is a negative 34. Okay. Now for this one, so now that becomes the last row of this augmented matrix, because we began by switching the first and third row. Okay. And we need to eliminate this number 3. So multiplying the first row by 3, okay, and add it to this row, then the first entry is going to be 0. Second, 2 plus 4 times 3, that is 14, and negative 12, and 30. Okay, so in order to transform this augmented matrix to this one, we used a row switching, and we used the row addition. Okay, and we need a number 1, so 1 pivot in the second row. And how to make this negative 13 to 1? Because we have 14 in the last row, so we can simply add the third one. We can simply add the third one to the second. Then this guy transformed into 1, 0, 0, 4, 1, 14. Sorry, just okay, negative 2 and 8, and negative 7, and negative 4. Because I add the third row to the second, the negative 34 plus 30, that is negative 4. Okay, and then let me use a the row multiplication, because I can see one common factor for the entries in the third row, that is 2. So I can divide the third row by 2 for simplification. So 14 becomes 7, negative 12 becomes negative 6, 30 becomes 15. Okay, so here I did A2 plus A3, one row addition in order to get number 1, so pivot in the second row. And I divide the third column by 2. All right, and now I can use the second row to eliminate the number 4 in the first row and number 7 in the third row. Okay, so then let me multiply first negative 4. So multiply the second by negative 4, and to add the first row, then it becomes 1, 0. Negative 7 times negative 4, 28. So add it to negative 2, then we get positive 26. Okay, and this is 24. And 0, 1, negative 7, negative 4. All right. And the last column, for the last row, we multiply the second by negative 7. So now, in order to kill this number 7 in the last row, okay, and then add it to the third row, then we get 0, 0, and negative 7 times negative 7, 49, added to negative 6 gives us 43. Okay, and remarkably, the last element also 43. Okay, then we can do, so we can divide the third row by 43, and this 243 becomes just 1 and 1. Okay, and then finally, now using this pivot, number 1 in the third row, I can eliminate 26 and negative 7 in the third column. Then we get reduced row echelon form. Okay, so once again, after dividing by 43, we multiply first the 7 and add it to the second row to kill this negative number 7. And then using row addition one more time, so now multiplying negative 26 and then add it to the first row. And you can kill this number 26. All right, then finally we get this one. All right, so now the coefficient matrix is in the reduced form. Each pivot is a number 1, and each column containing pivot has no other non-zero numbers. Okay, so satisfying the two conditions for being reduced form. So now we are done. So how do we interpret this? So the first one is, the first row is, the first column is x1. So that means x1 is negative 2 in the last column. So the first row, the entry in the first row in the last column. And the second row or second column is for x2. And we have just 1 in the middle. So x2 equals 3. And the third column is for x3. So x3 is 1. Okay? I mean, the way to interpret this is the same as the way to interpret this augmented matrix. This augmented matrix, for example, the first row tells us negative 3x1, 2x2, negative 6x3 equals number 6. Okay? So similarly, the first row, how do we read this? x1 and 0, 0. So we don't have to put the two variables. So this simply can be read x1 is negative 2, second row, x2 is 3, and the third row, x3 is equal to 1. All right? So this is called the Gauss-Jordan elimination method. Okay? It's quite reminiscent of, the standard elimination way when we solve a simultaneous equation systems. So, it can be thought of as the Gauss-Jordan elimination method formalizes, the standard elimination method in solving system of equations. All right. So we learned two methods of finding solution in a system of linear equation Gauss-Jordan and Cramer's rule. If we compare these two methods, and one comparative advantage of Gauss-Jordan elimination is, in order to use Cramer's rule, a coefficient matrix should be scalar. Otherwise, we can think of an inverse matrix, right? And it has to be non-singular, right? Otherwise, going back to Cramer's rule, if the coefficient matrix is a singular, then we can apply this rule because determinant of A is going to be 0. Right? So the Cramer's rule can be applied only when matrix A is a non-singular scalar matrix. On the other hand, this Gauss-Jordan elimination method can be applied to any type of coefficient matrix. Here is one more example, the final example. So use Gauss-Jordan elimination to solve the system. So we have two equations and three variables. So you can easily see the coefficient matrix is going to be non-scalar, is a rectangular matrix, 2 by 3. All right. So the inverse matrix does not exist, but the still Gauss-Jordan elimination method works. We have -4, 6, 4, and 4, the augmented matrix, and 2, -1, 1, 1. We can first switch the first and second. So using row switching, put the second row on the first row. Right? And how do you do this? I can multiply by 2. So I can multiply the first row by 2 and add it to the second. Then we can kill this -4. So 2 and 0, 4 and 6 and 6. Okay. Then now I can divide the second row by 4. Then it becomes 4 becomes 1. 6 becomes 1.5, and this is also 1.5. Okay. Now add the second row to the first. Then we can eliminate this number 1. So 0 and 2.5. Okay. And the leading entry, non-zero entry, should be 1. Then we just divide the first row by 2. Then 1, 0, 1.25, and 1.25. Okay. Now this is a reduced row echelon form because each pivot, so there are only 2 pivots because it's a 2 by 4 matrix. So each pivot is number 1, and the first 2 columns contains a pivot, right? And it has no other non-zero entry, right? And the way to read this equation is, this matrix is, so we have, let me delete this, and rewriting that reduced form. So 1, 0, 1.25, 1.25, and 0, 1, 1.5, and 1.5. Because we have 3 variables, from x1 to x3. So the first row says x1 plus 1.25 x3 equals 1.25. Okay. From this, we can deduce x1 is a function of x3. So x1 is 1.25 minus 1.25 x3. And from the second, x2 plus 1.5 x3 equals 1.5. So x2 is 1.5 minus 1.5 x3. So we can anticipate there are infinitely many solutions to this equation, right? For each value of x3, it gives, we have a different x2 and x1, right? And there is no restriction on x3. Right? So we have infinitely many solutions. But Gauss-Jordan elimination gives us some relation between variables in a very easy way, right? And can be applied to this kind of non-rectangular matrices. Okay, so that is it can be thought of as one comparative advantage of Gauss-Jordan elimination method relative to Cramer's rule. All right. So this is the what I prepared for the third video, and I think I have a 5 or 10 minutes. So let me call this the last video of the fourth week, and I have one more topic as application, and let me explain this. So let me cover this at the live lecture this Friday. All right. So hope you guys enjoy this video, and you guys have a great week. Enjoy the rest of the week, and see you guys at the Friday on the Friday.